students. I hope you are doing well. And now we have finished our part of the course which is related to images. Today we will be talking about sound. So let's see what is in this sound. So first of all, we will be discussing what is the nature of the sound, what is amplitude, what is the frequency, wavelengths, what is the frequency spectrum, and what is the waveforms. So we will discuss these topics which actually in which we are trying to find out the attributes of the sound, how it look like, how we can do some processing on it. Okay, so what are the learning outcomes of this session? Describing the fundamental properties of the sound, including the frequency, amplitude, and the wavelength. And we also need to know we will be able to describe what is a frequency spectrum, defining the and what is the human hearing range. I mean, what a human ear can hear. Describe sound wave interference and analysis and explain various waveforms. So nature of the sound, that is the first one. What sound is actually it is. So sound are produced by the conversion of energy. So we have some energy that we want to convert into a vibration in the air, or it can be another medium. For example, maybe water, maybe the glass, maybe the metal. So if we can produce the waveforms in that particular specific medium, whatever it is, maybe a solid, maybe a gas, maybe a liquid, then we can produce the sound inside it. So these vibrations are detected by the receiver. Of course, in our case, the receiver is our ear, and it is converted into the nerve pulses which go to our brain, and we experience that specific phenomena that we call sound. So when the what do you mean by the what you can say that the mean by the wave inside the medium, whether it is an air or whether it is a uh, liquid or solid. So actually it create a ripple effect somewhere. The if we look at that, that is a refraction means the particles of that particular specific medium are far apart, they are the spaces between them is higher. And the other part is called compression. It means the particles are compressed together in a small space. So compression and refraction, so that generates that particular, that is the form of the sound wave which is traveling in the medium. Normally it is air, but it can be a solid, it can be a liquid as well. And if we try to draw that particular specific wave in the sine wave form, then it will be like that. So it is the highest peak, the highest or the height, we call it a peak of this signal, that actually representing the compression, and the depth of that particular specific graph is representing the refraction, where the particles are far apart. So we have compression, refraction, and this way we can show that particular specific sound wave inside our graph system, inside our digital form, or the mathematical form, you can say that. So looking at that particular specific sine wave, we have certain specific properties which we can assign to that, to any sound wave. So we have an amplitude. Amplitude is actually from this middle line. If we have that particular specific middle line here, then the amplitude is the distance between the highest or the lowest point. Okay, so here we have a negative amplitude, here we have a positive amplitude. So the highest, the peak. Okay, so that is the amplitude, and the higher the amplitude, the higher the volume of the sound. Lower the amplitude, the lower the volume of. So amplitude is actually representing the volume of the sound. And then we also have the frequency, just like we have some frequencies, I mean how many frequency sound waves we are producing in 1 second, or any source. huh? Our mouth is a source of the sound. So if I speak, what are you doing? I'm having a good time. What are you actually doing? So I have increased the frequency of that particular specific source, or the frequent sound wave. So you are speaking very fast or you are speaking very slow. So that is representing how much frequency you are generating or the source of the sound is generating in one particular specific second. So that is the frequency. So amplitude representing the volume, frequency representing the speed of that particular specific wavelength. And then again we have a short wavelength. Wavelength is actually some if I let me bring that particular specific pen. If I say that this is our wavelength, the one, what you can say, that one wave. Okay, so we are starting at this particular point and then we are going up to this point. So this is the middle line, if you say that. Okay, so this particular red part is actually representing the one wave. So one wave, starting from the zero amplitude, go to the highest peak, go to the lowest peak, and then come back to that particular specific 0 point. So that is one wave, one um, which containing both the compression and the refraction. So that is the wavelength we're talking about. If we have a short wavelength mean that it is like this, more like this. So it is a short wavelength. It means that we are having the high frequency. The short length is less. It means that we are producing that particular specific sound wave in a very quick manner, the high frequency. And high frequency mean high pitch, which is very like shrilling sound. Okay, and on the other hand, if we have the wavelength which is long wavelength, it is will be something like this. If I say that, go up and go like this. So if we look at that, the here, this is our, what you can say, that the small wavelength, this one is our long wavelength. So you can imagine the other one, the longer wave I have drawn here. So it is a long wavelength. So it has low frequency, slow sound, and it will also have the slow pitch as well. So these are the few properties that we need to consider when we are discussing, when we are doing some analysis on the sounds: amplitude, volume, frequency, speed of that particular specific source. And then if we have a short wavelength is also important part. What is the length of that particular specific wave? Short wavelength, high frequency, high pitch, and long wavelength, it means that low frequency and low pitch. Okay, so now we come to the, because human ear is capable of detecting the frequency between the 20 hertz and the 20,000 hertz. Hertz is actually what you can say, that it is unit for measuring the frequency, 20 hertz, and the 20 kilohertz, 20,000 hertz. So that is the sound range, that is the range of the frequencies that we can hear. A normal ear can detect and can hear, can generate those things. But definitely as we grow older, that range is shrinking. So maybe some of you may not be able to see to hear the sound which is 20,000 hertz, or maybe 19,000 hertz, or maybe 20 hertz, or 30 hertz, or 40 hertz. So on this upper part, more or less it is going down. Okay, so that detectable sound range is shrinking with the age. However, this varies depending on the individuals. Okay, so this is normal ear. Depending on different individuals, that range can a little bit varied, maybe from starting from 100 to 1500 or 15,000 hertz, something like that. So interestingly, the upper limit decreases fairly rapidly. Upper limit decreases fairly rapidly with the increasing age. As the age is increasing, the upper limit is decreasing very rapidly. A few adults can hear sound as high as 20 kilohertz. Also, the children can. I mean, when you are young, you are a kid, you can hear that particular specific sound. But as you grow older, the upper range is going down very, very rapidly. So right now we are not in the class. Otherwise, I would have given you some play different sounds from our Audacity. Audacity is a software that we are going to use to do some manipulation, do some analysis, doing some changing some sounds. Okay, so You can access it freely. You can just download Audacity. It is at the end of the lecture. You can see its name as well. Okay, so because we are not there, so we can't do that particular specific experience, but you can do it in your home. You can play different sounds of different frequencies, and then see if you can hear it or not. Okay, fine. So this is some interesting hearing test. So if you can go to that particular YouTube channel, is low hearing and high hearing test, so you can see, you can do it yourself. Okay, then you see that if you can hear some sounds or not. So that will give you the idea that what is your range of frequency that you can hear. So the nature of the sound, I mean, 261.62 hertz note, that is a middle C. We are talking about some piano or some musical instruments, can be produced by many instruments like guitar, violin, voice, or piano, etc. So it is the transient behavior of the notes, that contribute to the unique sound of the instrument. I mean, we know that with these different instruments have different sound. So what that the transient behavior that actually what you can say that belongs to that particular specific instrument, that differentiate between their sounds. If the attack portion is removed from the recording of a single note, only the steady portion played, and obey guitar, violin, or the voice and the piano will be indistinguishable. So let me explain you a little bit more what is, and I mean, these are the different piano strokes. You can see that all have different frequencies, so you can see those frequencies here. What are those frequencies? Okay, so we can calculate the wavelength and so on. So tuning fork, let me go back a little bit, go forward, yeah, here. So I mean, they are saying that if we remove that particular specific attack node, then we if we are playing that particular specific sustained part, or the normal part which is sustained or having the same frequency, then we will not be able to distinguish between different sounds of the different instruments, different sounds of the different instruments. Okay, so what do you mean by the attack node? So when, for example, if we talk about the piano, that is true for our speaking as well. So when we press the key, when we press that particular specific key on the piano, it will take some time before it can reach the maximum amplitude of that particular specific note or the key press that you have, the sound that is being produced. It will take some time. It's very small time, but yes, it will take some time. So that part is called the attack node. If and then we are saying that if that attack node is being removed, because this is different for different instruments, then the sound will be exactly the same for different instruments, whether they are piano or the violin or the some other instrument. Okay, so that is what they are telling at that particular span. So when we press the key, it will take some time that it attain the maximum or the maximum amplitude. So that part is called the attack node, and then it come down for a some time, that is a decay part, and then it will sustain mean if you have pressed the key and keep on pressing, don't release that key, then it will go to the maximum amplitude, then it will come down a little bit and then sustain that specific frequency. Okay, a specific amplitude is going to be sustained for as long as we keep on pressing that particular specific key, and when we release the key, it will take some time that before that amplitude is going to zero again. Okay, so we have these, and this is true for our speaking as well. When we start speaking, it will take some time before we can attain the maximum amplitude, then it will sustain. If we continue our conversation, then our conversation sustain at a specific, maybe a range of frequencies, range of amplitude, but it will sustain at some specific time, and then when we stop speaking, our frequency is going to, I mean, amplitude is going to go to zero. So that what attack node they are talking about at this particular specific point. Okay, so let me go over. So I mean, if we remove that particular specific attack node, then we cannot distinguish between the different sounds of the different instruments. So this is, again, we are not going to discuss that. This is a piano difference. So tuning forks and the frequency generator. Tuning fork, that's that we have, that we can generate a specific uh, waveform in the air. Okay, and then we also have some frequency generator, cleanly produce vibration for at a single frequency, and that is what exactly we can do with our Audacity software. You can say that I want to generate a sound wave of a specific frequency for specific period of time, and you can play that particular specific sound. So most other sound vibrate in a more complex way. I mean, only the tuning fork or a specific frequency generator can produce the single frequency sound. But normally when we are talking, or when you are playing the piano, it is not the single frequency which is being generated. Okay, so you are pressing the multiple keys, you are doing a lot of when you're talking about, your pitch is going up and down, your frequency is going slow and fast, your wavelength is getting changing out. So most of the sounds which are vibrate in a complex way, and it's a combination of different frequency components, because we are not uh, when we speak, we don't produce the same frequency sounds at same at all the time. It is changing with maybe on your mood, on your expression that you are giving it, the frequency is changing. So actually the sound is a complex combination of different sound frequency components. So the combination of the frequency component is called frequency spectrum. So what are the different frequencies which are present in the actual sound which we are hearing or which we are producing? So in other words, most sounds are combined or combination of the bunch of different wavelengths. So different frequency components are combined together in one waveform, and that is the normal sound we hear. So again, these are the individual notes frequencies. Okay, so if you can see, I mean, we can see these are the C major piano, then we also have a D minor piano. So we have all the frequency as well. So we have the C note, the name of the note, and then we also have the frequency, what frequency they are showing. So when we have consider that this is the source one which is producing a specific sound wave or at a specific frequency, this is another second speaker which is producing the same frequency, not the same, but a different frequency sound wave. So we have speaker 1, speaker 2, which are speaking at the same time, and now once their sound waves are combined together, we can have two different type of effects. The first one is the constructive effect. It means that if you look at that, the amplitude is a little bit low here, it is amplitude is a little bit low here, but when they combine together, they are combining in such a way that it is increasing their amplitude, increasing their effect, increasing their volume, you can say that. So you are actually hearing a higher sound, which is a louder sound as compared to the original sound of the speaker 1 and speaker 2. Okay, so that is kind of a constructive effect, where the two frequencies or two frequency components, two wavelengths of different frequency combine together in such a way that it increase the amplitude of that particular specific sound. So then we call it a constructive interference. They are interfering, they are mixing together, but in a constructive way. Okay, they are increasing the volume. On the other hand, if we have the two speakers and their waves income such a way that the compression or the higher amplitude exactly match with the lower amplitude, and the lower amplitude exactly match with the higher amplitude of the other wave, they cancel out the effect of each other. Cancel out means that you will not hear anything. They are making that particular combined frequency waveform, the amplitude of the combined waveform, to be zero. It means that you cannot hear anything. The amplitude of the resulting wave is zero, and that is called the destructive interference. Sometimes it is not like your compression is exactly matching the refraction, and then they are canceling out the effect of each other. So sometimes it is not that, maybe a little smaller amplitude. I mean, you can say that two waveforms combine together, but in such a way that the amplitude does not become zero, but it decrease from the original sound. It's again a destructive interference. Okay, this is the perfect form of the destructive interference, where the exactly they are coming at the same time, the compression and the refraction of different sounds, and they canceling out the effect of each other, subtracting each other, and the amplitude becomes zero. But this is an ideal situation, but it is possible that. So two type of interference we talk about. One is a constructive, when the amplitude of the combined wave increase, and the second one is destructive, when the amplitude of the combined wave is decreasing. So that is constructive and destructive type of interference. For example, another one, so we have 40 hertz, we have 50 hertz. So we are playing 40 hertz sound frequency, wave with the 40 hertz frequency, 50 hertz frequency, and when we combine together, some part are constructive and some parts are destructive. Okay, so here we have a constructive interference where two waveforms are combining together and producing a constructive interference effect. On the other part, they are producing the destructive interference effect. And look at that, it's the amplitude not becoming zero, but it is lesser, it less than the original sound waves. Okay, so these are the constructive and destructive. So we are only combining two different sound waves. One is a 40 hertz and the other one is the 50 hertz frequency. And this is actually what we can say the combined wave, or we can say that is a frequency spectrum of these two sound waves. I have already explained you that attack node and the decay node, sustain and all. Okay, so interesting sound change over time. The sound change over time. We have attack node, we have a decay, then we have sustain, and then we release that particular specific key. The frequency spectrum change as it grows and decays. Grows mean we are talking about the decay, and attack, and then decay mean that this particular specific part. Sound that extend over time, over longer period of time, have a constantly changing frequency. When, as I told you, that when we are speaking, the our frequency is changing all the time. Okay, so constantly changing frequency spectrum. So we can display the waveform of a sound by graphical plotting its amplitude against time. So these graph that I have showed you here, they are actually the, we are plotting the what is the amplitude of the sound at a specific time. So the amplitude is going up, then it's coming down, up down, up down. This is this waveform of the violin, this is a trumpet, this is a flute, this is a oboe. Okay, so we have different type of we have graph for different type of instruments. This is again a teenager speech. So you can see this is the plot that we can see in our Audacity as well. So when you will start using that particular specific software, then you will be able to understand what's going on. This is again another sound wave for another sound source. This is this classical piece of violin. Again, what is the sound sort of sound violin, cello and the piano. So what will be the sound wave? I mean, we have three different instruments we are playing, a classical music. Okay, and then you can see their sound waves. Again, how the sound wave of the seas, they are again still producing different type of sound waves. And then you can, if you want to start to record it and plot it inside the Audacity or some other software, then you will see something like this. Again, in the Audacity, that is the software that we're talking about. You can search on the Google, and then it's freely available. You can download and you can install it on your home PCs or your laptops, and then you can see. And we can zoom in the, I mean, we can zoom. This is sometime it's not like that, but if we try to zoom it, then you can see that it will be something like this. You can see those waves over there. Okay, so that is the end of our lecture. So what we have studied in this lecture, that what are the fundamental properties of the sound, like frequency, amplitude and wavelength, and what is the frequency spectrum, what is the normal hearing range of a human ear, and then what are the interferences when the multiple sound frequency components combine together and produce the actual sound. So what are the different type of interference? Constructive interference or the destructive interference, and then we have different type of the waveforms. Okay, so that is all for this lecture. Okay, have a good time. Bye.